This video is about properties of logarithms and exponents, and then some practice with problems that might include log properties. All of these are a review, basically, except for maybe one or two of them. So we're going to go through them relatively quickly. Log base a of 1. This could be log base anything of 1. That's 0. Because remember, logs and exponents are inverses, and a to the 0 power is 1. So log base a of 1 has to be 0. Log base a of a is 1, because a to the first power is a. A to the log base a of m, since those are inverses, the a and the log base a invert each other and cancel each other out, basically. And so the answer would be m. And that is a really poor looking m. So is that. I'll give it one more try. None of them were good. Log base a of a to the r. Remember that the exponent inside of a logarithm can move to the outside. So this would be r times log base a of a, and we know that log base a of a is 1. So this is just r. Then we have properties where we have products on the inside. So log base a of m times n, we can expand that to log base a of m plus log base a of n. Likewise, if it's division, we can expand it and turn it into a subtraction problem. So log base a of m minus log base a of n. And both of these, all of these, but both of these, numbers 5 and 6 especially, will often be used in reverse. So I can ask you to condense, starting with something like this and moving it that way. Number 7, e to the r natural log of a. This isn't so much a property, it's more just a problem where we can kind of figure out what's happening. Remember that if I have an exponent and I can move it out to be a coefficient, I can take the coefficient of r natural log of a and turn it into an exponent. So I'm going to rewrite this as e to the natural log of a to the r. And e to the natural log, those are exponent, or those are inverses, so those go away. So I basically just end up with a to the r. Log base a of m to the r, we've already talked about this, but this r can move out to the front, so it's r times log base a of m. And the change of base formula is kind of a new one. So log base a of b, I don't really use this that much in, we use it quite a bit in problems, but it's not something that you have to use nearly as much because your calculator does log bases now, but you can choose this to be log base anything of b divided by log of that same base times a. So you can make this log base 5 of b over log base 5 of a. You can make it log base 2 of b over log base 2 of a. You can make it natural log of b over natural log of a. There's a lot of different ways that you can do this, but it's log base whatever you want as long as that base is the same. So log base n of b over log base n of a. Here's a quick review of some exponent properties. X to the a times x to the b is x to the a plus b. X to the a to the b power, you multiply the exponents. So x to the ab, x to the 0 is 1, x to the negative a is 1 over x to the a. And A result of that is if I have something like x over y to the negative a, that's y to the a over x to the a. So I can just take the reciprocal. And then x to the a divided by x to the b is x to the a minus b. All right, a few problems. Log base b of xy over z squared, we have to expand this. So let's go back. That would be this property or this property. So all of these are going to be in terms of log base b. So log base b of x plus log base b of y minus log base b of z squared. And I can expand it even further because this 2 can move out to the front. So my final answer would be log base b of x plus log base b of y minus 2 log base b of z. Condensing means I take something that looks bigger and then smush it down, kind of going in this direction. So the first thing I'm going to do is take the coefficients and turn them into exponents. And then my final answer will be to condense these things. So I end up with log base 2 of a b cubed over c to the 1/2, which is the same thing as the square root of c. And we could rationalize that denominator, make it ab square root of c over c if we want. So now we're going to use a lot of change of base formula. So if I want to rewrite this using a base of 3, I'm going to rewrite this as log base 3 of 27 over log base 3 of 9. So I just rewrite the 27 on top, the 9 on bottom, and I choose the base I want. And then it doesn't ask us to do this, but we can easily simplify this. Log base 3 of 27 is 3, log base 3 of 9 is 2. So this answer would be 3/2. If we use a property of logs with the same base and a plus, I'm going to rewrite this as log base 12 of 3 times 4, which is 12. Log base 12 of 12 is 1. Now this one looks pretty intense. What I'm going to do is I'm going to use the change of base formula here. So I'm going to make all of these things log base 3s. So log base 5 over log base 3 of 5 over log base 3 of 3 times log base 3 of 7 over log base 3 of 5 times log base 3 of 4 over log base 3 of 7. So I'm just looking at the first part of this here at the moment. Notice when I do that, some of these things end up canceling off. And log base 3 of 3 is 1, right? So this whole thing over here was just log base 3 of 4. I can use the exact same situation. Yellow may not be the best choice. For these, so I'm going to choose log base 3 again And the reason why I'm choosing log base 3 is I kind of know what the answer is. But even if you didn't choose log base 3, at the end you could use a change of base formula again in order to get what you need, choosing whatever problem you have. Sorry, I'm trying to talk and write at the same time. Log base 3 of 12 over log base 3 of 6. And notice that these cancel, this is 1. So I end up with log base 3 of 12. Likewise, I have a subtraction, but I have log base 3 of 10 over log base 3 of 3 times log base 3 of 16 over log base 3 of 7 times log base 3 of 7 over log base 3 of 10. So notice a lot of these things cancel. Log base 3 of 10, log base 3 of 7, log base 3 of 3 is 1. So now what I have is I have log base 3 of 4 plus log base 3 of 12 minus log base 3 of 16. Since all of these have the same base, I can use the condensing property to multiply 4 times 12 and then divide it by 16, all inside of a log base 3. So 4 times 12 over 16 is all on the inside. And 4 times 12 over 16 is 48 over 16, which is 3. So I end up with log base 3 of 3. So this whole problem was just 1. And that makes me kind of annoying that I wrote this entire long problem and the answer was 1, but such is life. Final 2 problems, some solving. So these are condensing problems. So natural log x plus 2 plus natural log of x minus 3 is the natural log of these two things multiplied together. So that's x squared minus x minus 6. Then since I have a natural log on both sides, the insides have to be equal to each other. So x squared minus x minus 42 equals 0. If I factor this, I get x equals 7, and x equals negative 6. But x equals negative 6 can't be an answer because it doesn't work in either one of these. I'd have negatives on the inside of the log. So the answer is just x equals 7. Then my final problem is a similar one. So there's a minus, so when I condense this, I get log base 2 of x plus 3 over x minus 4 equals 3. And then I would just rewrite this in exponential form. So x plus 3 over x minus 4 equals 2 to the third. 2 to the third is 8. And then I can cross multiply here because it's an equal sign. It's not a greater than or equal to or a less than or equal to or anything. So I can multiply this x minus 4 over as long as I remember that 4 is a domain restriction. So x plus 3 equals 8x minus 32. So 7x equals 35. And 35 divided by 7 is 5. And I check that in my problem, and I realize that I am allowed to plug in 5 for both of these, so it ends up working out.